Hello everyone, this is Vijetha, Associate Professor from the Department of ECE from MLR Institute of Technology. Today I would like to have a talk on Introduction to Verilog-HDL from the subject Linear and Digital Integrated Circuits. These are the topics which I want to cover here, that is Introduction to HDL, Verilog has HDL, and what are the levels of design descriptions which are used to write a Verilog code. Now we'll see conventional approaches to digital designing. What is a conventional approach for digital design and what are the advantages and disadvantages of conventional approach to digital design? So the word digital has made a dramatic impact on our society. The most significant is a continuous trend towards a digital solutions in all areas from electronic instrumentations, control, data manipulation, signal processing, telecommunication, etc. to consumer electrons. Development of such solutions have been possible due to good digital system designs and modeling techniques. So the digital evaluation starts from designing a good digital design systems and modeling techniques. This is one of the conventional approach to digital design. So the first step is system requirement. It decides the requirement at the system level. The system requirement decides the requirement at system level. And the second one is circuit requirements, where it translates system level to a circuit requirement. Next, the circuits can be designed either by using ICs or other components or maybe some functional blocks. So the major identifies over this part is maybe a functional blocks which are like timers, DME units and register files, or ICs like counters, multiplexers, demultiplexers, etc. or some SSI signals, that is small scale integrated circuits, for example like gates, flip-flops, or maybe some transistors, diodes, resistive, capacitor components can be used in this part to design a circuit. So the conventional approach starts from the system requirement, then it goes with the circuit requirement. Then based on the circuit requirement, either you can choose a functional blocks, or you can choose a standard ICs, or you can use a small scale integrated circuits, or you can choose a transistors or active and passive components based on the circuit requirement. After that, after choosing all the components, then we'll go with the PCB layout, wiring and testing, and final circuit. Where in PCB layout and wiring and testings, the physical location of all components is tentatively placed. That is, rough placement will be done in PCB layout. The physical location of all components is tentatively decided. That is, rough placement of all the circuits have been placed on a printed circuit board, where they are interconnected on a circuit on paper is made ready. Once the paper design is done, layout is carried out and net list is prepared. That is, wiring and testing is going to be starting after placement of components on a PCB. Based on this, PCB is fabricated and populated. All the populated parts tested and debugged. This procedure shows in the flow chart here. The final circuit can be come out after placement of all the components on a PCB designing, then connecting the components through a wiring, then it went to a testing, then final circuits will be coming out. So, what are the disadvantages of using this conventional approach? The disadvantages of conventional approach is dealing with the debugging stage. So, what happens in debugging stage in conventional approach? So, in debugging state encounters with the three types of problems. The first one is functional mismatch. The realization and expected functions are different. This may have to go through the relevant functional block diagram carefully and locate any errors logically. Finally, necessary connections has to be carried out in a hard way. The second one is timing mismatch. The problems can be manifested in different forms. The first possibility one is due to a signal going through a different propagation delays in two paths arriving at the same point with a timing mismatch. This causes a faulty operation. The another possibility is race condition in a circuit involving asynchronous feedback. This kind of problems can be elaborate debugging. The preferred practice is to debugging a smaller module stage and ensuring the feedback through a larger loop is avoided. It becomes essential to check for the existence for a long asynchronous loop. We have two different problems over here. The third one is overloading. Some signals may be overloaded to such an extent the signal transmission may be unduly delayed or even suppressed. The problem manifests as a reflections and erratic behavior in some cases. In fact, overloading on a signal can lead to a timing mismatch. The above have to be carried out after completion of prototype PCB manufacturing. It involves cost, time and also redesigning process to develop a bug-free design. So, if you want to design a bug-free design, time constraint is more over here, the cost is also high and redesigning process will be happening for multiple times. These are the disadvantages which are having in conventional design approach. Now, complexity of VLSI design. The complexity of VLSI being designed and used today makes a manual approach to design impractical. Design automation is the order of the day. The rapid technology development in last 2 decades, the status of VLSI technology is characterized by the following. A steady increase in size, hence the functionality of IC increases. A steady reduction in future size, hence the speed of the operations as well as gates or transistor density is going to be increasing. A steady improvement in predictability of circuit behavior. A steady increase in variety and size of software tools for VLSI. The above development has resulted in new approaches to VLSI, which is aimed to bring out the role of hardware descriptive language in a design process. This is how HDL has come into picture. In conventional approach, you need to start designing with the components, fabrication, later testing. Whereas in HDL code, you can write a HDL code, you can check the output and you can dump the HDL code into your FPGA kits or CPGA kits. You can check the outputs. So this is an advantage of using a HDL instead of conventional approach. This is an ASIC design flow and development flow. First, you need to know the idea. Then you can write a design description for the idea, and the design description can be done either of these 4 levels like behavioral level description, data flow description, gate level description or switch level description. These are the 4 levels of design description. You can use any of the 4 design level description to write the Verilog code over here, HDL code. Then after completing the design description, it can be simulated or it can be synthesized. Whatever the synthesis record can be given to a physical design. So the idea first comes to an idea, then idea can be implemented by using a HDL code, then HDL code can be simulated and synthesized, and then we can give it to a physical design. Here the elaborated ASCII design have been shown here. First you need to know the idea, then you need to draw the, you need to take the HDL code, then which can be given to a synthesis, then you can dump into FPGA codes, then you can check the output. Then after completion of this of this HDL language, you can do the placement of your circuits. After finishing HDL code, after writing HDL code and checking the HDL code output, you can place the components on a floor, that is placement of components on a PCB. Then it can be placed, routed, then this can be done parallelly with a verification. So, the placement of a circuit, routing to the circuits can be verified parallelly, then you can get the final circuit. This is a ASIC design flow. Verilog as an HDL. Verilog has a variety of constructs which are aimed at providing a functionally tested and a verified design description for target FPGA or ASIC. The languages has a dual function. One is to fulfill the need of design description. The other one is to fulfill the need of verifying the design for functionality and timing constraint like propagation delay, circuit path delay, slacks, setups and hold times. There are 4 levels of design description. The components of a target design can be described at a different levels with the help of constructs in Verilog. There are 4 levels or 4 constructs in Verilog. First one is gate level, data flow, behavioral level and circuit level, which is also called as a switch level. The first one is gate level. At this level, design is carried out in terms of basic gates. All the basic gates are available as ready modules called primitives. See, here I have taken example of AND gate. So, we'll have a primitive called AND, which will be followed with outputs, then inputs. So, this is AND is a primitive. The syntax of primitive is AND followed with output, followed with inputs and end with semicolon. So, the basic gates, basic logic gates are available as a ready module called a primitives. Each such primitive is defined in terms of its inputs and outputs. Primitives can be incorporated into design description directly. You can use these primitives can be directly used into a design. A full physical hardware can be built using a gates. The primitives can be used repeatedly to build a larger system. If you use n number of primitives, the simulation time may increase. The figure shown an AND gate is suitable for description using a gate primitive of Verilog. The gate level modeling or structural modeling as it sometimes helps to build a digital circuit on breadboard or on a PCB. One should know the structure of design to build a model here. One can build hierarchical circuit. One can also build a hierarchical circuit at this level. If we have a 20 or 30 such gate primitives in a circuit, the design description becomes bulky. Testing and debugging. If we have a more than 20 or 30 such gate primitives, the design descriptions becomes bulky and the testing debugging becomes laborious. That is, it is very difficult for testing and debugging the 30 or 40 such gate primitives. The next level design description is data flow. Data flow is the next higher level of abstraction. All the possible operations on signals and variables are represented here in terms of assignment, and all the logic and algebraic operations are accommodated. The assignments defines the continuous function of a concerned block. At data flow level, signals are assigned to the data manipulation equation. All such assignments are concurrent in nature. The design descriptions are more compact than those at a gate level. An example of AY relation suitable for description with a Verilog construction at data flow. You can use all arithmetic and logical operations to write a Verilog code in data flow, and you can use an assignment structure which helps to link the inputs to the outputs. This is one of the example which I have shown here to take a equation in a data flow. The next level is behavior level. In behavioral level constructs the highest level of design description. The behavioral level constitutes the highest level of design description. It is essential at system level itself. With the assignment possibilities, we can use looping structures and you can use a conditional branching possibilities, and the design description essentially looks like a C program here in the behavioral level. You can use a for loop, you can use a while loop. You can use a if condition or if else condition to write a HDL code, Verilog-HDL code in a behavioral well, which similarly looks like a C program. The statement involves or dense in function. Compactness and comprehensive nature of the design descriptions makes the development process fast and efficient. So, the simulation speed can be increased when we are going with the looping or conditional statements. The below equation shows an AOA gate expressed in pseudocode suitable for description with the behavioral level constructions of Verilog. V is equals to A dot B plus C dot D. This can be either you can write in a gate level, or you can write in a behavioral level, or you can write in a data flow level. But the simulation time taken in behavioral level will be less comparing with the gate and data flow by using a loop conditions and if conditions. Circuit level. The fourth one is circuit level designing. At circuit level, a switch is a basic element with which digital circuits are built. Switches can be combined to form an inverter and other gates at next higher level of abstraction. Verilog has a basic MOS switch built into its constructions, which can be used to build the basic circuits like inverters, logic gates, 1-bit dynamic and static memories. They can be used to build a larger design to simulate at circuit level and to design performance critical circuits. The figure shows here is an example of an inverter for a switch level constructions. Q1, Q2 are the transistors where Q1 is used in a pull down network and Q2 is used in a pull up network. The NMOS and PMOS, let us assume this as an NMOS and let us assume this as a PMOS circuit. So, this NMOS and PMOS can be available. The MOS switches, the NMOS switch and PMOS switch is readily available. The figure shown here is an example for circuit level switch. It's an inverter which has been using a two transistors Q1 and Q2. These are MOS transistors. So, this is going to be working as a switch. So, these MOS switches are readily available in a Verilog. We can use those MOS switches to design a Verilog code in a circuit level designing. So, we will write a code for the circuits in a circuit level designing. Summary. First, how HDL have been developed. So, initially we used to have a conventional design approach. Here, you need to start the design from a physical layout, from physical design. We need to start from the physical design, then you need to check. So, the disadvantage here is redesign, cost and timing are the main factors in conventional design approach. So, HDL has came into picture to reduce the time and cost and redesigning. This hardware description language has been introduced. Like first we can write a Verilog code, not only Verilog code, you can use VHDL code also, but here in our syllabus we have VHDL codes. That is why I am choosing a Verilog code. So, you can write a Verilog code, then you can test the Verilog code, then you can dump into FPGA kits, then you can check the output. Then you can go with the physical layout like placement, routing, fabrication, everything can be done after checking the Verilog code. If you have any errors here, you can check the Verilog code again until you get the correct output. Then you can go with the placements. So, the cost and timing factor is going to be reducing here by doing a HDL code placements and routing and fabrication. And the next is in HDL language, we have a 4 levels of design descriptions. First one is gate level, where you can use a primitive to write a Verilog code. All the logic gates are available in terms of primitive. Second one is we have a data flow. where you can use in data flow design, in data flow level, you can use all assignments. You can use all assignments like logical and arithmetic operations. So you can use the operations in writing a Verilog code in a data flow. And the third one is behavioral level, where you can use a if or if else, like conditional statements or conditional, or you can use a third one is behavioral, where you can use if that is where you can use a conditional statements, or you can use a loop statements to write a behavioral code, which is similar to a C language. And the fourth one is circuit level designing, where you can write a, you can have a MOS switches. We can have a MOS switches where you can write a code for the circuits, that is transistor level designing. You can write a code for transistor level design. All the MOS switches are available in a Verilog code. You can call the MOS switches to write the circuit level designing. Thank you.